All right, welcome. We are starting a new chapter today, chapter 16 in the Burge book. This is on acids and bases, and we're going to talk about properties of acids and bases and pH, pOH, acidity constants, and we're going to do some equilibrium problems. So it's important that you know the material from the previous chapter on how to write equilibrium expressions and be able to manipulate those to solve for either equilibrium concentrations or an equilibrium constant. So we're going to use that knowledge and apply it to determine pH, like what is the pH of an acid in equilibrium with water? What's the pH of a base? What's the pH of salts? So all of this stuff is going to come into play. To me, this is probably one of the most important application chapters. I do think you take this with you to other courses, and it's important that you understand it. Like, you're going to be talking about pH in your other courses, and where does the pH scale come from? How is it derived? What are your strong acids and bases in water? There's going to be some memorization required there. And then we're going to look at weak acids and weak bases. And then this conjugate acid base pair is really important, and it's kind of, sometimes students have difficulty understanding it. And the reason why this section is important is that we're going to use this along with acids and base knowledge to work on buffers in the next chapter, buffers and titration. So, important chapter. It really sets the foundation for the next chapter, which is on buffers and titrations. All right, so first let's talk about, here's some, again, there's the salts. That's what I was talking about. And we're not going to cover Lewis acid, bases, and salts. You will get this in an organic class, so that's why I'm not concerned about covering Lewis acids and bases. All right, first topic is Bronsted acids and bases. So Bronsted is there are different theories for acids and bases. All right, so the simplest theory, which you should have been exposed to in chemistry 170, Gen Chem 1, is the theory that anything that generates the hydrogen ion is an acid, and anything that generates the hydroxide ion is the base. And this was Arrhenius's theory. And so Arrhenius was the person who determined that there were such things as ions. He was one who determined that sodium chloride actually consists of sodium ions and chloride ions. So naturally what he did here was he noticed that things that had acidic properties, like taste sour, generated the hydrogen ion, and things that taste bitter, which is a property of bases, generated the hydroxide ion. But the problem with Arrhenius's theory, one of the things is like ammonia. When you look at ammonia, you don't see any hydroxide there. So for weak acid or weak bases, it was hard for him to determine just by structure if it was going to be a base or not. So since most of the chemistry we do in Gen Chem is in water, we're going to look at acids in this way. So an acid, this is hydrochloric acid. How do you know it's an acid? Well, again, Gen Chem 1, you should have talked about acids and bases. This is called a binary acid. And if you don't remember anything about acids, what I would tell you to do is I have a video on naming acids and bases. I would look at that video on my Professor Chemistry channel. And then I would look up the section prior to this one, like back to chapter 3 or 4. about acids and bases, because at this point everyone should recognize that HCl dissolved in water, so hydrogen chloride dissolved in water, is called an acid, and the name of this acid is hydrofluoric acid or hydrochloric acid. And the reason why we call it hydrochloric acid is because it's a binary acid. It's got a hydro prefix and an X suffix. So again, if you don't know that, you're going to have to go back and refresh your memory about that. But notice what happens here. This hydrogen ion is donated to the water, and then the water becomes the hydronium ion. So if you don't know, this is called the hydronium ion. Again, you're going to have to go back and refresh your memory, because we're going to be using this a lot, and you got to speak the language. So this is what gives acids their chemical properties. Taste sour, turn blue. Litmus, which is a vegetable dye, to red. They tend to be corrosive. They tend to form carbon dioxide when added to a carbonate. Those are all different types of properties about the acid. And then we have names for these two products, and you're going to need to be able to speak the name. This is called conjugate, and I'm just going to write CONJ, acid. And what is left of the hydrochloric acid is the chloride ion. That's called the conjugate base. So it's important that you can identify the conjugate acid and the conjugate base. So those will be on the product side. Conjugate acid, whatever accepted the hydrogen ion is called the conjugate acid. Whatever lost the hydrogen ion is called the conjugate base. Again, something covered in Gen Chem 1, Chapter 3 or 4. Make sure you look back at that. Just brush up, because we assume that knowledge, and now we're going to talk about, and we assume the knowledge of the last chapter, how to deal with equilibrium problems, and now we're going to apply it to determine pH or pOH. In this second chemical equation, we have ammonia, and the way we know it's a base is we can see that the water donates the hydrogen ion to the ammonia. We get the ammonium ion, NH4 positive. So that accepted the hydrogen ion, so it's called the conjugate acid. And again, the water lost the hydrogen ion, so what's left is the conjugate base. So I'll just say CB here for short. So what's neat about this is water can act as both an acid and a base. In this first equation, water is acting as a base because it accepts the hydrogen ion. And in the second equation, water is acting as an acid because it's donating the hydrogen ion. So that's the definition of a Bronsted acid and base. A base is a hydrogen ion donor or proton donor. That's an older term. Let's see, did I say that right? An acid is a proton donor, or hydrogen ion donor. And a base is a proton acceptor or a hydrogen ion acceptor. All right? So ammonia is the base; it accepts the hydrogen ion, and hydrochloric acid is the acid because it donated the hydrogen ion. And then the aftermath, what's on the product side, be able to label what is your conjugate acid and what is your conjugate base. Really important. It's not hard to do. Whatever gained the hydrogen ion is now the conjugate acid. Whatever lost the hydrogen ion is the conjugate base. So here's some species of acids and their conjugate bases. So here's a formic acid, and here's the hydrogen. And so this is a carboxylic acid. When you see this double OH, this is an organic carboxylic acid. When we remove the hydrogen ion, what we have left over is the formate ion. And you got to speak the language. Again, it's called formic acid over here, and it's called the formate ion over here. We have water. It donates a hydrogen ion. What we have left on the water is the hydroxide ion. There's my conjugate base. Here's ammonia. This is the one I think the students have the most trouble with, and this is going to be an important one. So we have ammonia. It loses a hydrogen ion. It can do that. We just saw that it can act as a base and accept a hydrogen ion, but ammonia can also lose a hydrogen ion in certain conditions. And we get the NH2 negative ion. And so keep that in mind. I think that's called the amide ion. And then we have sulfuric acid, loses one hydrogen ion, and now we have the hydrogen sulfate ion. So again, these are all conjugate bases. All that's happened here is we have removed a hydrogen ion from the acid. It's very easy. All right, so then we can have conjugate acids. So here we see ammonia can act as a base, which we just saw 2 slides ago. So it accepts a hydrogen ion. Anything that accepts the hydrogen ion, what it forms is called a conjugate acid. So there's the ammonium ion. Water accepts a hydrogen ion, becomes the hydronium ion. The hydroxide ion accepts a hydrogen ion, it becomes water. And then we have an organic substance, urea. And this is the important part of urea right here. And it accepts a hydrogen ion, and then we get this urea ion. All right, so these are all these substances on this side have accepted a hydrogen ion, and they are called conjugate acids. So you know it's important if they're spending multiple slides on this, all right? And then they show us again what this looks like. What we've already drawn, which is here we have the acid. It loses a hydrogen ion. What we have left is the conjugate base. So hydrochloric acid loses a hydrogen ion, and the chloride ion becomes the conjugate base. The water accepts the hydrogen ion, becomes the hydronium ion, and that's the conjugate acid. And we'll do the next one, which we've really already done this. So I'm not going to spend a lot of time, but again. Ammonia is acting as a base here because it accepts the hydrogen ion, and then it becomes the ammonium ion. That's the conjugate acid. The water lost a hydrogen ion. What's left is the conjugate base. All right, so let's check this out. You should be able to answer these fairly quickly. These shouldn't take that much time. So it says, what's the conjugate base of nitric acid? You would say nitrate. You lost a hydrogen ion. What's the conjugate acid of O2 negative? And you would say OH negative, because conjugate acid means we've added a hydrogen ion, right? Conjugate base says we've taken one away. So conjugate base of this would be SO4 2 negative. And the conjugate acid, you got to read these carefully. The conjugate acid of the bicarbonate ion would be H2CO3. So see how fast that is? It should be that fast for you. If it's not, you got to do more of them. Base, take away the hydrogen ion. Conjugate acid, add the hydrogen ion. All right, very easy, very easy. All right, let's talk about the acid-base properties of water. So water is a really special substance. We know it is. We see it all the time in chemistry. I mean, water is a unique substance, and it is so special. In fact, we believe it has to be present in order to have life. So water can act as, so again, we're going to make this reversible. For some reason, this slide is not showing the full... It's not showing the double arrows there. So remember, double arrows from the last chapter means it's a reversible process. And so it works here. It's working perfect here, so I'm not sure. So if I was going to write water like this as an equation, this is the Arrhenius way of showing it, right? It just shows that water ionizes into a hydrogen ion and a hydroxide ion, all right? And we call that auto-ionization of water. And Arrhenius knew about that. So auto-ionization of water. The way that Bronsted would show it, he'd actually show it as 2 waters. And if you don't like the way this looks, you could say H2O plus H2O. But one water accepts a hydrogen ion, the other water loses a hydrogen ion. And so that follows Bronsted's definition of an acid. And this is what it looks like. Again, this being the acid donates a hydrogen ion to this water. And what we have left is the conjugate acid. And then what's left over of the water that donated the hydrogen ion is the conjugate base. So we call a substance that can act as a Bronsted acid or base amphoteric. All right, so you need to know that word. Amphoteric means that it can act as a Bronsted acid or base. Water's the most common one to discuss. Ammonia is the next most common. So ammonia can gain a hydrogen ion and become the ammonium ion. We've seen that already. Or it can lose the ammonium ion and become the amide ion. So we've seen that. We've already seen that. But we're going to focus on the autoionization of water. The autoionization of water is the foundation of the pH scale. So here we go. So what we've learned from our previous chapter is that if this is my balanced chemical equation, that I can write the equilibrium expression for this. And so the equilibrium expression is the equilibrium constant times the concentration of the hydrogen ion. Now, I don't know why they didn't do this. I would, if you're going to write it this way, okay, here it is, right? But if you're going to think of it in terms of a Bronsted acid and base, you would have written it like that, right? And you would have gotten this equation. So they mean the same thing. And I will say, a lot of times, even though we're saying Bronsted acid and base, we will write it this way because it's easier to write, more compact. And we know that this hydrogen ion is attached to water. All right, so I'm not going to focus too much on that because I do see it written that way a lot. But technically, if you want to write it as Bronsted acid-base theory, this is the way to do it. So we know that those brackets mean equilibrium concentrations. We know that it's in moles per liter. And so this equilibrium constant is so special, it gets its own little subscript. We've seen Kc means equilibrium concentration. We've seen Kp, which is equilibrium at pressure. And now we have Kw, called the ion. When we multiply this together, this number here is what it should always come up to be at 25 degrees Celsius. And we call this the ion product constant of water. So again, you need to know the language. Ion product constant for water is 1 times 10 to the negative 14th at 25 degrees Celsius. So in pure water at 25 degrees Celsius, since both of these things are generated by the water molecule, then in pure water, the hydronium ion and the hydroxide ion concentration should both be 1 times 10 to the negative 7th molar. You said, how'd you get that? Well, since both of these ions are generated by one water molecule, then these are both going to have the same concentration if it's pure. All right? And when we multiply those, we add the exponents together, so that's how we get this number here at 25 degrees Celsius. So in pure water, these have the hydronium ion and hydroxide ion concentrations have to be the same. When we multiply those together, we get the ion product constant of water, which is 1 times 10 to the negative 14th. Really important to know. You're going to be doing this a lot where you're going to say, I'm going to do the shorthand notation, the hydrogen ion concentration times the hydroxide ion concentration equals 1.0 times 10 to the negative 14th. And then I'm going to be solving for one or the other. Given one of these concentrations, I can solve for the other one. So that's where we're going with this. Also, you can see here, you know that pH 7 is neutral. So look at that. There's this 10 to the negative 7th, and that is the concentration of both of these substances when in pure water. And there's going to be a relationship between the ion product constant of water, or the ion product constant expression for water, and pH 7. So that's where we're going with this. All right, so when the hydronium ion and hydroxide ion concentration are equal, 1 times 10 to the negative 7th, then we say the solution is neutral. When the hydronium ion concentration is greater than the hydroxide ion concentration, the solution is acidic. And when the hydronium ion concentration is less than the hydroxide ion concentration, the solution is basic. What I want you to remember is at 25 degrees Celsius, when you multiply this number times this number, it has to equal 1 times 10 to the negative 14. So they're tied together here. If this one goes up, this one has to go down in order for it to equal 1 times 10 to the negative 14th when you multiply them. That's where we're going. So let's look at this one. It says the concentration of hydronium ions in stomach acid is 0.10 molar. So we are in moles per liter here. Calculate the concentration of the hydroxide ions in stomach acid at 25 degrees Celsius. Notice they say 25 degrees Celsius because we know the equilibrium constant, which is called the ion product constant for water, is 1 times 10 to the negative 14th at 25 degrees Celsius. So these are easy problems too. You know the hydronium ion concentration. You're asked to solve for the hydroxide ion concentration. So you divide both sides by the hydronium ion concentration to get the hydroxide by itself. You plug in the hydronium ion concentration, the 0.10 molar, in the denominator there. And we get 1 times 10 to the negative 13th molar for the hydroxide ion concentration. Again, really simple problem. This is not the difficult. Everything I hope that we've done so far in this chapter is like, oh yeah, this isn't too bad. Now we get to the pH scale. So the pH scale is based on this. So P stands for negative log. So that's what I want you to remember here. P stands for the mathematical function negative log. And you go, why do we have that? Well, it's much easier to write P than it is negative log every time. So P is a quick way to represent a mathematical function. And so pH means negative log of the hydrogen ion concentration, which technically, according to Bronsted-Lowry definition, or Bronsted definition, it's negative log of the hydronium ion concentration. All right, so if we have a neutral solution, we know these two concentrations are equal and they're both equal to 1 times 10 to the negative 7th. We multiply that together, we get 1 times 10 to the negative 14th. So that's why these both have to be 1 times 10 to the negative 7th. So for the hydrogen ion concentration, or hydronium ion, I plug that into this equation. And that's what we said. pH is equal to negative log of the hydronium or hydrogen ion concentration. So what does the log do? So if you don't remember logs, you need to go back to the appendix in the back of the book, and they do a whole little section. You've probably already seen it because we've been dealing with natural logs when we did kinetics. Well, here we're using a log base 10, and you should know that the log of 1 is 0. And then, so we're going to say the log of 1 is 0. We're not worried about that. And then negative log of 10 raised to the negative 7th power. Well, the log is the inverse of the exponent. And so when we take the log of 10 raised to the negative 7th, we get negative 7. But then this negative out here is a correction factor to make that a positive 7. So that's why our answer for the negative log of 1 times 10 to the negative 7th molar is equal to 7. All right? You have to be able to do this. You have to be fluent in this. So how do you get fluent in it? Maybe in a while since you had college algebra, something or equivalent. So you're just going to have to practice. All right. So in a neutral solution, where both the hydrogen ion concentration and the hydroxide ion concentration are 1 times 10 to the negative 7th, the pH is 7, so that's neutral. So what you know is that the pH scale is going to go from 0 to 14. You go, how do you get 14? Well, let's look at that. Let's look at the relationship. The hydrogen ion concentration times the hydroxide ion concentration has to equal 1 times 10 to the negative 14. So if the hydrogen ion concentration is 1, that makes the hydroxide ion concentration 1 times 10 to the negative 14. And if I take the log of 1, we know that's 0. So if I take the log of 1, we know that's equal to 0. So that's the bottom of the pH. And again, we're taking the negative log of the hydrogen ion concentration. And then the alternative is the hydrogen ion concentration is 1 times 10 to the negative 14th. And the hydroxide ion concentration is 1. And that, again, will equal 1 times 10 to the negative 14th at 25 degrees Celsius. So if I take the negative log of, and I should have done that. There's a negative up there too. I just didn't worry about it because I know it's 0. But the negative log of 1 times 10 to the negative 14th is going to give me 14. So that's how we get the upper scale. So upper scale is 14, lower scale is 0. 7 is neutral. We just saw that. So if the pH is greater than 7, that means the hydroxide ion concentration is greater. All right. And so this is called a basic solution. If it's right at 7, we know it's neutral. And if it's less than 7, that means that the hydrogen ion concentration is larger than the hydroxide ion concentration. So we call these solutions down here acidic. All right. So the lower the pH, the more acidic. That's what I want you to get straight, because I see students make mistakes on this all the time. The lower the pH, the more acidic. The higher the pH, the more basic. And 7 being neutral. All right, so we put this in a table, and it looks like this. So again, their scale goes from bottom to top. So we have a PA, we have a 10th molar hydronium ion concentration. Take the negative log of that. Log of 1 is 0. Log is inverse of exponent, pulls the negative 1 down, but then remember it's negative log. Don't forget the negative there. And that makes that a pH of 1. So notice as the concentration of the hydrogen ion decreases, we go less, the pH goes up, and then we finally get to neutral. So notice as the pH increases, we know that the hydrogen ion concentration is decreasing. Then we get neutral, its own special place right there. And then as the hydrogen ion concentration continues to decrease, that means the hydroxide ion has to increase. So I'm going to write that like this. That means the hydroxide has to increase. All right. I don't know if I want to write it that way, but it's increasing. And we see the pH continues to increase here, which means less acidic, more basic. Okay. So look at this slide. It's in your PowerPoints as well, but you've got to get a good feel for it. Bottom line is ion product constant of water, the hydronium ion concentration times the hydroxide ion concentration has to equal 1 times 10 to the negative 14th. So as the hydronium ion concentration decreases, the hydroxide ion concentration has to increase. When there's more hydroxide ion than hydronium ion, it's a basic solution. When there's more hydronium ion than hydroxide ion, it's an acidic solution. And if they happen to be both the same, then we have a neutral solution. So here are some common pHs. So stomach acid, about 1.5 pH, very acidic, right? Lemon juice, 2.0. Vinegar, 3.0. Grapefruit juice 3.2, orange juice 3.5. You know, my dentist says anytime I have a fruit juice or Coke or whatever, it says always follow up with rinsing your mouth out with water, because if you don't, the acidic solutions rest on the gum line and they start eroding the enamel on your teeth, and over 50 plus years you'll start to see it. It's on the. I have some of that, so she's always saying, Brent, make sure you drink some water after you drink coffee or orange juice or things like that. Then we have urine. So we can test your urine. This, when we start seeing things out of whack in the urinary system, it'll show up in the pH. Rainwater. Now rainwater, a lot of people think, oh, it should be right at pH 7. Well, when carbon dioxide dissolves in rainwater, it makes an acidic solution. That's why clean air rainwater is going to have a pH of 5.5. Now, acidic rain, acid rain is 4.0, and so they go, well, that's only 1.5 difference. Well, my question to you, if you want to stop here, if you want to really think about this, how many more times is acid rain acidic than rainwater at 5.5? So what does this mean? The difference here is 1.5 pH units. What does 1.5 pH units translate? How does that translate into concentration of hydrogen ion or hydronium ion? Okay. So stop and think about that. I would stop and see if you can figure that out. If you can, that means you've mastered pH and you understand what it means. Then we have saliva, we have milk, we have pure water, we have blood. Notice your blood's a little acid, a little basic. Then we have tears, milk of magnesia, and then household ammonia. Household ammonia is pretty strong there. pH goes up to 14. We're only 1.5 away, or 2.5 away from 14, right? All right, so you got to be able to do the inverse. So again, this is just a math problem. So if you have negative log of the hydronium ion concentration is equal to the pH, and I want to get rid of the log. How do I do that? Well, I do the inverse. I do the exponent. So I'll move the negative over to this side and then raise both sides 10 to that amount. And that gets, this is the inverse of that. And now I have, if I flip, I have the hydronium ion concentration is 10 raised to the negative pH. So you need to be able to use that equation. So both of these equations, this one and this one, you need to memorize. And you'll have them memorized through the course of doing these problems. All right, so here we go. It says determine the pH of the solutions. They're all at 25 degrees Celsius. Why are they saying that? Because at 25 degrees Celsius, you know the ion product constant of water is 1 times 10 to the negative 14th. And that's what pH is based on. So these are all hydronium ion concentrations. These are all H3O positive concentrations in moles per liter. Okay. So to get the pH, we know the rule is the negative log of that concentration is equal to pH. So this is very easy. So on your calculator, you're going to say negative. You're going to hit the log button on your calculator, and then you're going to put in the number, and then you're going to close the parenthesis. I think you have to do that, and then hit enter, and it'll give you the number. Now, while you're doing these, I hope you will look at these numbers and see if you can kind of figure out what the ballpark should be for the pH. So here's what I know. I know that if the concentration of the hydronium ion is 1.0 times 10 to the negative 4, the pH is 4. All right? That's easy. This is 0, and the inverse of 10 to the negative 4 is negative 4, and then we got the negative here, so it's going to be 4. All right? So when I see 3.5 times 10 to the negative 4, I know the pH is going to be like 3 point, it's going to be 3 point something. It's going to be lower than 4 because this number is greater than 1 times 10 to the negative 4. So I don't know if this was down to it's between 1 and 10 here, right? This could be between 1 and 9 or whatever, 9 0. So we're closer to 4. So we're probably up on the upper end. I'm going to guess 3.6. All right, that may be a bad guess, but that's what I guess. Same thing here. This is even less. So we know 1 times 10 to the negative 7th would be a pH of 7. This is 1.7. So I'm going to guess it's going to be high up on the higher end, right? So I'm going to say 6.8 or something like that. And then this one, it's almost 1 times 10 to the negative 10th. That's almost there. So, this 8 is 8.8. Then we have 9.9, and then this thing, if it becomes a 10 here, this becomes 1 times 10 to the negative 10th. So I'm going to say this is pretty close to 10.0. This number is so large, between 1 and 9, it's very close to that. And as this number increases, we're getting more hydrogen ion, and we expect the pH to deviate negative of this number. So it's not going to be 1 times, if it was 1 times 10 to the negative 11 to be a pH of 11, this is pretty close to 1 times 10 to the negative 10, so I'm going to expect the pH to be pretty close to 10. because we know anything greater than 1 times 10 to the negative 11th, it's going to be in the 10 region. And then because this is so close to 1 times 10 to the negative 10th, it's going to be pretty close. But you don't have to do, I think if you can kind of figure those out in your head, kind of look at that and go, yeah, the first one's going to be less than 4, second one's going to be less than 7, third one's going to be less than 11, and then kind of get a gauge for that. I think it helps you catch mistakes. So if you work that out, it's fine. If not, just make sure you plug it in the calculator correctly. So here's our answers. The first one I'm off. I went the opposite way. It said 3.5. So, I just think that would be closer to, it's not, 1 to 9, it's that way. I don't know. I think it's a little strange. All right. Let's plug it in. I want to see that one real quick because I am a little like, I thought I would be closer than that. So let's say, here it is. You just put negative in your calculator, hit the log button, put in a 3.5, and then put in an exponential negative 4, close the parenthesis, hit enter. Yeah, it is 3.46. All right. Okay. The rest of them okay. All right, so then you got to do the reverse. And this one, you're given the pH is at 25 degrees Celsius, and you have to find what the pHs are, or the hydrogen ion concentrations, or hydronium ion concentration. This is more proper. So you just say 10 raised to the negative 4.76. Here's what you got to remember. This has to deal, the number in front of the decimal has to deal with the power of 10. The number after the decimal has to deal with this part, okay? So 4.76, we know that it's going to be, that's like 0.76, this, we know it's going to be like it's going to be 10 to the negative 5th, right? Same thing here. This is a negative 11.95, pretty close to 12, and this is 1.1 times 10 to the negative 12. This one here is negative 8.01. That's going to make it 9.8 times 10 to the negative 9. So again, you can kind of get these numbers just by looking at what's after the decimal. But if you can't, that's okay too. Just plug it into the calculator correctly, and you should get these types of values. So I would plug these in, make sure you're using the calculator correctly. All right, easy problem. So these are easy. I mean, on a test, you shouldn't spend much time on the problems we were doing so far. They're pretty quick. All right, then we have the same thing for POH. So POH, P means negative log. So here we have that. And instead of the hydronium ion concentration, we have the hydroxide. The inverse of that is the hydroxide ion concentration is 10 raised to the negative POH. So not that difficult. Just make sure that you're answering the correct. Are they asking for pH or POH? And what's the relationship? Well, here's the cool thing. I love this slide here. So we know that the ion product constant of water is the hydronium ion concentration times the hydroxide ion concentration has to equal 1 times 10 to the negative 14. We're going to take the log of everything on this line here. So again, if you don't remember, when you multiply negative logs, you add them. So that's why you can do this, that the log of the hydronium ion concentration plus the log of the hydroxide ion concentration. So again, if you don't know this, make sure you go back in the appendix and look at that. Just like if it's division, it's subtraction here. So then we multiply everything through by negative. Don't forget that. And that makes negative log of the hydronium ion concentration minus the log of the hydroxide ion concentration. And negative log of 1 times 10 to the negative 14th is 14. And then what's cool here is that this is the definition of pH. This is the definition of POH. So when you add pH plus POH, it has to equal 14. All right? So know this equation. It makes things go a lot faster. pH plus POH at 25 degrees Celsius must equal 14.00. All right, so then I show you some examples of POH. So what you notice is at low POHs, the solution is very basic. Just like low pH is very acidic, low POHs is basic. High POHs means the substance is acidic. It's just the, it's the same thing, right? pH of 1 is acidic, pH of 13 is basic. Flip it, POH of 1 is basic, POH of 13 is acidic. All right, determine the pOH in which the hydroxide ion concentration, so, you might want to draw that. They're telling you these are hydroxide ion concentrations. So what do? We plug these values into our equation. pOH equals negative log of the hydroxide ion concentration. And that's what they're doing here. And you might want to stop here and see if you can guess what the answers are going to be. Like the first one, it's going to be lower than, it's going to be a pOH of 4 point something, right? The other one's 3.5, so I'm going to guess this one is, 4.4. Let's do that. And the next one, 4.1, 6 something, 6.2. And the next one, that's pretty close to 9, so I'm going to say 1.0, since that other one was like that. All right, but plug that in your calculator, and there's the actual pHs. Oh, let me point out something here. Let's go back. I want to do something here. Let's talk about significant figures, because I see students get dinged for this all the time. Okay. So these are concentrations. These are concentrations. And they all have two significant figures. These are concentrations. They all have two significant figures. All right. So let's look at our answers. These are our pOHs. So the first number has to do with the power. This has nothing to do with significant figures. Anything to the left of the decimal has to do with power and not significant figures. Since all of our measurements had two significant figures, you notice there are 2 digits to the right of the decimal, So this is where we get our significant figures. All right? So let's go back. When you make a measurement in concentration and it has 2 significant figures, like we see here, then you should have 2 digits to the right of the decimal in your pHs or pOHs. Make sure you know that, all right? Because I do see students, like the calculator, put out some number like 4.3987, I don't know, whatever it is. But that would say you'd have 4 digits in your concentration measurement. And we didn't have that. We only had 2. So watch your significant figures. I do think you get the wrong answer if you put the wrong significant figures on the connect. And then you're going, I know I'm doing this right. Why is it wrong? It's probably your significant figures. All right, then the opposite. We just saw this with the other one. We know that the hydroxide ion concentration is equal to 10 raised to the negative pOH. And here's what we do. This first number all has to do with the power. The second 2 numbers have to do with how many significant figures in our measurement. So we would expect 2 significant figures in each one of these concentrations when we're done. So again, plug 10 raised to the negative 4.91, 10 raised to the negative 9.03, 10 raised to the negative 10.55, and our answers are to 2 significant figures, 1.2 times 10 to the negative 5th, 9.3 times 10 to the negative 10th, 2.8 times 10 to the negative 11th molar, respectively. Easy stuff. I'm telling you, this is easy. All right, strong acids and bases. I think I'll do this and then we'll call it quits for this video. So it's important that you memorize your strong acids in water and your strong bases in water. I can't stress it enough. It's not that much, but if you don't memorize these, you're going to have no shot at getting all the problems right on this section and the next chapter. So what is a strong acid? A strong acid is not treated as an equilibrium, but a process that goes 100% to completion. So the way we draw that is hydrochloric acid, when, let's do it the Bronsted way, when added to H2O liquid, again, this donates a hydrogen ion to the water becomes the hydronium ion, aqueous, and then we have the chloride ion, aqueous. This reaction goes 100% to completion. The arrow only goes in one direction, 100%. All right? So there's no equilibrium here. Equilibrium means it's reversible. It can go back and forth. That doesn't happen with the strong acids. They go 100% to completion. So if this is 0.10 molar hydrochloric acid, at the end of this reaction, if you did an ice table, this would be minus I should say minus 0.10, and the equilibrium value would be 0. Over here, you would have 0 plus the gain of 0.10, and so the equilibrium value would be 0.10 molar. And then you take the negative log of that, and you get a pH of 1. All right? So 100% of the acid ionizes in this case, because this is a molecular acid. 100% of it ionizes. All of this is consumed. All of it's formed here and here. We're not so interested in the conjugate base yet, especially for strong acids. But I want to know what the pH is. All I have to do then is take the concentration we had here. We know it's a 1-to-1 relationship between hydrochloric acid and hydronium ion. So I take the negative log of 0.10 and I get a pH of 1. All right? That's what happens with the strong acids. So you go, well, what are my strong acids? Well, here they are. You have to memorize this page. It's not that many. There's just 7. The first 3 are called binary acids. That's why they have the hydro prefix and the X suffix. And actually, we talked about this in Gen Chem 1. It was so important that I had my students memorize the strong acids in water in Gen Chem 1. Then we have nitric acid. And then we have perchloric through sulfuric. So really these, I don't know why I pointed, nitric acid is a strong oxidizing acid, but so is some of these, so I don't know why I did that. But so here's the dividing line as far as the ones below this line are oxyacids, and the ones above it are binary acids. And if you've had my class, you know the mnemonic for these oxyacids is I ate something icky. So this is the nitrate ion, that's its conjugate base. This is the chlorate ion, this is the perchlorate ion, this is the hydrogen sulfate ion. So when we add a hydrogen ion to these oxy ions, the acid ends in ick. So I ate something icky. If the polyatomic ion ends in ate, the acid ends in ick. I ate something icky. All of these ions end in ate. All of these acids end in ick. So you memorize these 7 strong acids. And the reason why you want to memorize these 7 strong acids is because anything other than these 7 are going to be considered a weak acid. So if you don't memorize these 7 and you see something like acetic acid, and I'll write it the way an inorganic chemist would write it. That's one way to write it. The other way to write it would be CH3CH2OOH. All right. So that's not one of these 7 strong acids. So acetic acid would be a weak acid. And this is the acid that's in vinegar, acetic acid. So memorize these 7. I can't stress that enough. Know both their names and their chemical formulas. Otherwise, you're going to get lost. So strong acids go 100% to completion. And so here's what they want you to do. They tell you what the concentration of the acids are. All right. You know they all only have one acidic hydrogen. That's important to know. All right. So if they go 100% to completion, this is going to be the concentration of the hydronium ion at equilibrium. That's what you need to remember here. Strong acids, these are all strong acids. They go 100% to completion. So since it's 1 mole of hydrogen ion, then that is going to be the concentration of or 1 mole of the acid, then that's going to be the concentration of the hydrogen ion and therefore we just need to take the negative log of those numbers there. Makes it real easy. Again, fast. Here they are. Since they're all monoprotic, they only have one acidic hydrogen, the concentrations that we just saw are the concentrations of the hydronium ion. Plug those into our pH equation, and now you have the pHs of those acids. Very easy. Again, very quick, very easy. All right, so then just the opposite. We've already seen this over again too. The only twist is now we're talking about a strong acid, hydrochloric acid. So whatever the pHs are, these are attributed to the hydrogen ion concentration. So if I take negative 10 raised to the negative pH, that will give me the hydrogen ion concentrations and the concentration overall of the hydrochloric acid. So you can speak it two ways. Since HCl is 1-to-1 with the concentration of the hydrogen ion, or the hydronium ion if you want to do it that way, whatever the concentration of this is the concentration of the acid. All right, and so there they are. Again, not a difficult problem. All right, your strong bases. Now, the strong bases, everyone agrees, anything out of group 1 or group 1A, either way you want to think of it. If you say group 1, it's the modern numbering system of groups on the periodic table 1 through 18. The American system, group 1A, still the first group, first vertical column. Every hydroxide out of group 1A is a strong base. So lithium hydroxide, any metal hydroxide out of group 1. Notice hydrogen's not here because hydrogen's a nonmetal. We have sodium hydroxide, we have potassium hydroxide, and so forth. These are all strong bases. Now, out of group 2, the heaviest of the alkaline earth metals are strong bases. So let's look at it. And again, I want you to follow what this book does because that's what you're being tested on. So in group 2, some books will say these two are only strong out of group 2, but this one also includes the calcium hydroxide. So out of group 2, this is the trickiest part. You have to memorize these three. Everything out of group 1, strong, but out of group, and they don't put francium because whatever it's. But anyways, because it's radioactive, I don't know if they have even good measurements for that. But anything out of group 1 is a strong hydroxide, is a strong base. And these three out of group 2, just memorize those. They're all down at the bottom, towards the bottom of the periodic table, so it's not hard. But I just find sometimes students miss these, and it's not hard. It's not hard. Just memorize those three, and the rest of them are group 1. So that's what happens. Notice the arrows only go one direction. This is not called dissociation. These were ionic compounds to begin with. All that's happening, this is not called ionization. These are ions to begin with. This is called dissociation. So speak the language. Whereas hydrochloric acid, it was a molecular compound and it becomes ionized. So this is called ionization. We talked about this in Gen Chem 1. These are ions to begin with. All that's happening is they're being separated, and that is called dissociation. So speak the language. Speak the language. As with strong acids, because the reaction goes to completion, the pH of a strong base solution is relatively easy to calculate. All right, I love this problem here. So I want you to stop and I want you to calculate the pOH of everything here, A, B, and C. Go ahead and do it, and then when we come back, I want to talk about it. All right, so we're back. So what I would tell you to do, and if you do this, you'll not make any mistakes. If you draw this like this and say, okay, that forms a lithium ion and a hydroxide ion, and whatever this concentration is the concentration of the hydroxide ion. And then we go to the next one, you go, oh, that's a barium 2 positive ion plus 2 hydroxide ions. So whatever the concentration of this is, it's twice for the hydroxide ion concentration. And that is the most missed problem. I even seen it today. If this is on the exam, I see a lot of students miss this problem. The reason why they miss it, they're not writing anything down. You have to write this stuff down. I can't stress that enough. If you write it down, you won't make the mistake. All right? So this is the most missed problem. Even talking about it today, it's the most missed problem on the exam because students are in a hurry and they don't write their stuff down. They try to just do it in their head or on the calculator. Don't do that. Write every problem down. Watch the units cancel out. See what's going on. Don't do it in your head. So what you're going to see is that the concentration of the hydroxide ion is twice. It's twice, right? 2 times the concentration of the barium hydroxide. Because for every one of these, you get 2 of these. So now we've doubled the concentration of the hydroxide ion. So that's what we're going to take the negative log of. So this one's easy. This one is the tricky one, and the last one, because it's 1 to 1, 2, that's also easy to do. Just take the negative log of 9.2 times 10 to the negative 5th. And when we do that, we get those pHs. So if you didn't get this pH here, we know what happened. Don't make that mistake again. And that's why they did this. See this one? They both had the original concentration of the base being the same, but hey, because it's 2 times as much hydroxide, the pH is low. The pOH is lower. The pOH is lower. Yeah. All right. So let's read this one. Aqueous solution of a strong base has a pH of 8.15 at 25 degrees Celsius. Calculate the original concentration of the base in the solution. So let me tell you what this problem is. It's a stoichiometry problem. So you know I had stoichiometry in Gen Chem 1. This is nothing more than a stoichiometry problem. So first one, you know that sodium hydroxide ionizes 100% into sodium ions and hydroxide ions. And you know barium hydroxide is a strong base. So barium hydroxide completely ionizes into a barium 2 positive ion plus 2 hydroxide ions. So they tell you what the pH is. So what are you going to do to calculate the original concentration of the base in the solution? So they want to know what are the original concentrations of these bases. Sodium hydroxide, barium hydroxide. So before you use a calculator, let's do a plan of action. You know that pH plus pOH has to equal 14. All right? So if I want to know what the pH is, or pOH is, I want to say pOH equals 14 minus the pH. Okay? So the pOH of sodium let's do it this way, of the hydroxide ion in sodium hydroxide is 14 minus 8.15, which is I should be able to do that in my head, right? 5.85. 5.85. Let's just check it to make sure. 8.15. Yeah. 5.85. All right. 5.85 is the pOH for sodium hydroxide. The pOH of barium hydroxide is equal to same thing, right? 5.85. Okay, so they both have the same pOH. Duh. Okay, so you know how to convert that to the hydroxide ion concentration. Go like this: hydroxide ion concentration equals 10 raised to the negative pOH. All right, I'm running out of room, so we'll stop right there. But you know how to do that. We're putting us all together and doing a real problem. All right, so here we have it. Okay, and then here's where they emphasize it produces 2 hydroxide. And this is the most important step right here. So this one comes straight out. Whatever the hydroxide ion concentration is the concentration of the base. But this one, if you go back to that balanced chemical equation, barium hydroxide ionizes into a barium ion plus 2 hydroxide ions. You see the ratio is this. I have the hydroxide ion concentration. I've determined it. Here it is. But the hydroxide ion concentration, what we know is for every 2 moles of hydroxide ion, I get 1 mole of barium hydroxide. And so that's why they have the 1/2 here. But you should write it out. If you will write this stuff out, you won't make careless mistakes. Like some people look at this 1/2 and they say, where does the 1/2 come from? Well, if you wrote it out, you would see, and you did your mole to mole ratio of your balanced chemical equation, you'd easily see where the 1/2 comes from. So if you're one of those persons that didn't know where the 1/2 came from, that tells you that you got to write it out. You've got to write it out to check your work. And I would tell everybody to do that. Because in the end, in science, everybody's got to be able to follow your work, and the more steps you show, the easier it is for people to follow. And I know some people don't show enough steps. It's kind of an arrogant thing. I feel like, oh, you don't need to see every step. You just need to see the major steps. I don't think so. The people that just need the major steps, they'll skip over this, but it's still there for everybody else to follow. So it's important that you write your work out, and you've got time to do that. All right, that's where we'll stop at today, and we'll pick up on this on the next video, which will be, this is what we'll focus on. So this is all about equilibrium, constants, and expressions, and determining equilibrium concentrations of either the hydrogen ion or hydroxide ion. In this case, the hydrogen ion, because we're talking about acidity constants. And it's really doing equilibrium problems like we did in the previous chapter, just applying it to acids. So that's where we're stopping. Thank you.